There is a bicycle frame material that does not rust, does not fatigue under normal riding loads, does not need paint, and will almost certainly outlive the person who buys it. It has been available for more than 50 years. Almost nobody rides one. Walk into any bike shop in Europe or North America and count the titanium frames on the floor. In most shops, the answer is 0. Look at a professional road race, and you will not find a single one in the peloton. And yet ask experienced cyclists what they would buy if money were not a concern, and titanium comes up again and again, spoken about with a kind of reverence that no other material receives. So something does not add up. Either titanium is not as good as its reputation suggests, or the bicycle industry made a mistake that lasted 20 years. And the answer to that question decides whether the 4,000 euros a titanium frame can cost is a rational purchase or a very expensive story you are telling yourself. Here is what makes this worth investigating properly. The usual explanation is that titanium is simply too expensive, and that carbon fiber is the cheaper compromise most people settle for. That explanation is comfortable, it flatters anyone who owns titanium, and it is wrong. Titanium did not lose on price alone. It lost on engineering, in a specific and measurable way, and understanding exactly how it lost tells you more about buying a bicycle than almost anything else you could learn. Let us start with the claim that sits underneath every titanium conversation, that it rides better, that there is something in the metal itself, some springiness, some quality of feel that other materials cannot reproduce.
This belief is old, it is widespread, and it is the reason most people consider the material in the first place. There is a number in materials science called specific stiffness. It is simply a material's stiffness divided by its density. In other words, how much resistance to bending you get for every gram you carry. And when you calculate it for the 3 metals used in bicycle frames, something surprising happens. Steel, aluminum, and titanium all land in essentially the same place. Steel is about 3 times stiffer than aluminum, but steel is also about 3 times denser. Divide one by the other and the advantage disappears. Titanium sits in the middle on both counts and lands in the same place again. Within a few percent, these 3 metals are identical in the only ratio that matters for a bicycle frame, which means the material, by itself, does not make a frame stiff, it does not make a frame soft, it does not make a frame comfortable. If you take a steel frame, an aluminum frame, and a titanium frame that weigh the same and have the same tube shapes, they will behave far more similarly than anyone selling you a frame would like you to believe. What actually determines how a frame behaves is the tubing, specifically the diameter of the tubes and the thickness of their walls. And here is the part that explains why frames of different materials look so different from each other. Stiffness in bending rises with roughly the 4th power of tube diameter, while weight rises with roughly the 1st power. Make a tube fatter and thinner, and you gain enormous stiffness for very little weight. That single relationship is why aluminum frames use big fat tubes with thin walls. Aluminum is light enough to allow it.
It is why steel frames use narrow tubes with thicker walls, because steel is dense, and a fat steel tube would be unbearably heavy. And titanium, sitting between them in density, gets moderately oversized tubes. Every material is being used at the dimensions where its properties can be made to work. So when a titanium frame feels different from a carbon race bike, the metal is not doing most of that work. The geometry is different. The wheelbase is usually longer. The tubes are round rather than aerofoil. The frame was probably designed for endurance riding rather than criterium racing. Almost every design variable has changed, and the material is only one of them. There is a related claim about damping, the idea that titanium absorbs road vibration in a way other metals do not. Titanium does have somewhat higher internal damping than aluminum. Whether a rider can feel that difference through a tire, a wheel, a saddle, and a pair of gloves is genuinely contested. What is not contested is that tire volume and tire pressure change transmitted vibration by a far larger margin than any frame material does. If comfort is what you are buying, wider tires at lower pressure will do more for you than 4,000 euros of metal. So if the ride quality argument does not hold up, what does titanium actually do better? Because it does do things better, and this is where the material earns its reputation honestly. The first is fatigue. Every time you push on the pedals, every time you hit a pothole, every load your frame absorbs is a stress cycle. Steel and titanium share a property called every single cycle, no matter how small, contributes to eventual failure. That sounds alarming, and it should be put in proportion. Aluminum frame designers know this perfectly well and compensate by keeping working stresses low, which is why aluminum frames use more material at the joints and around the bottom bracket. A well-designed aluminum frame will very likely outlast your interest in it. But the failure mode is real, it is documented, and it usually shows up as cracking at a weld near the head tube or the bottom bracket after many years of hard use. Titanium, designed to stay below its fatigue limit, does not accumulate that damage. This is the genuine engineering foundation of the lifetime frame claim, and it is not marketing. But be precise about what that protects you from. The fatigue limit applies to the base material under controlled loading. It does not protect you from a bad weld. It does not protect you from a crash. It does not protect you from a stress concentration created by poor design at a dropout or a tube junction. Titanium frames do fail. When they do, they almost always fail at or near a weld, and the cause is manufacturing quality or impact damage, not the metal getting tired. The second real advantage is corrosion, and this one is not contested by anyone. Titanium forms a thin oxide layer the instant it meets air, and that layer repairs itself continuously. Road salt does nothing to it, coastal air does nothing to it, sweat does nothing to it. There is no internal frame preservative to apply, no paint chip that becomes a rust problem, no reason to fear a wet winter. If you ride through salted winters, or live near the sea, or commute year-round, this is not a theoretical benefit. It is a cost you are currently paying that would simply stop. Although there is a catch that titanium owners learn the hard way. The frame does not corrode. The interface between the frame and your aluminum seat post absolutely can. Put two dissimilar metals together with water between them, and you get galvanic corrosion, and a seized seat post in a titanium frame is one of the most common and most expensive ownership problems in the category. Anti-seize compound at every metal interface is not optional advice, it is a maintenance requirement. So we have a material that survives fatigue, ignores corrosion, needs no paint, and can be repaired by a skilled frame builder. That is a genuinely excellent set of properties. Which brings back the question that started all of this. If it is that good, why did the industry walk away from it? The answer has two halves. The first is an engineering advantage that carbon fiber has and that no metal can ever match. Metals are isotropic. That means their properties are identical in every direction. A titanium tube is exactly as stiff resisting one load as it is resisting another, and there is nothing a designer can do about that. Carbon fiber composite is different. It is anisotropic, and crucially, the designer chooses the direction of that anisotropy. Fibers can be laid along the specific paths the load actually travels, at different angles, in different quantities, with different fiber grades, in different regions of the same tube. Think about what that allows. A carbon frame can be made extremely stiff exactly where stiffness matters, around the bottom bracket where your pedaling force goes in, and around the head tube where steering precision comes from. And in the same frame, it can be made deliberately compliant exactly where comfort matters, in the seat tube, the seat post, the seat stays. A metal frame cannot separate those behaviors nearly as cleanly. The designer has only three tools: diameter, wall thickness, and shape. That is not a marketing claim. It is the defining structural property of composite materials, and it is the reason carbon took over the performance end of the sport. It also delivers on weight in a way that is not close. A titanium road frame typically lands somewhere between 1,300 and 1,700 grams. A good carbon road frame is often under a kilogram, and elite race frames are well under 700. That gap is real, and it is not disputed by anyone. Now be honest about the magnitude. 500 grams of frame weight on a system of rider plus bicycle weighing perhaps 80 kilograms is well under 1%. On a long climb, that is seconds over an hour, not minutes. For most riders, on most rides, it is not the thing standing between them and their goals, but for someone racing at the margin where seconds decide outcomes, it is exactly the thing. And there is a second performance gap that gets discussed far less, which is strange because it is larger. Above about 25 to 30 kilometers an hour, aerodynamic drag becomes the dominant force you are fighting. Most of that drag is your body, but the frame contributes. Carbon can be molded into deep aerofoil tube sections, truncated profiles, fully integrated cockpits with every cable hidden inside. Shaping titanium into those profiles is difficult, expensive, and almost never done. Round tubes are aerodynamically ordinary. So for the rider who spends real time above 30 kilometers an hour, the aerodynamic penalty of a round tube titanium frame is more consistently significant than the weight penalty. That is the strongest engineering argument against titanium for a fast rider, and almost nobody makes it. But go slower and the picture inverts. On a gravel road at 22 kilometers an hour, with rolling resistance and surface losses dominating, the aerodynamic gap shrinks toward irrelevance. Which is exactly why titanium found a second life in gravel while it was disappearing from road racing. That covers the engineering half of the answer. The commercial half is where the real story lives, and it is the part almost nobody explains. Titanium is difficult to make things from. Not moderately difficult, fundamentally, structurally difficult at every single stage. Start with the raw metal. Titanium ore is abundant, but turning that ore into usable metal requires a batch process that is energy-hungry and chemically demanding, and it has stubbornly resisted the kind of continuous high-volume industrialization that made steel and aluminum cheap. The metal arrives at the workshop costing many times what steel or aluminum costs per kilogram. Then you have to cut it. Titanium work hardens as you machine it, and it conducts heat poorly, so all the heat generated by cutting stays concentrated right at the tool edge. Tooling wears fast. Cutting speeds have to stay low. Every operation takes longer than the same operation in steel. Then you have to bend it, and titanium springs back. Push a tube to a shape and it partially returns. Butting a tube, which means varying its wall thickness along its length to save weight, is routine and affordable in steel. In titanium, it is difficult and expensive, which is why many titanium frames use tubes that are straight gauge or only lightly butted, and why they carry weight they theoretically did not need to. And then you have to weld it, and this is where the economics really break. At welding temperature, titanium reacts aggressively with oxygen, nitrogen, and hydrogen. Let any of them reach the molten metal, and the weld becomes brittle. So welding titanium properly is not one process, it is 4 simultaneous ones. The joint must be scrupulously cleaned. Argon must shield the torch. Inert gas must be flowing inside the tube behind the weld, purging it. And a trailing shield must protect the weld and the surrounding metal while it cools. There's a beautiful detail here that you can actually see. A correctly executed titanium weld comes out silver or straw-colored. As contamination increases, the color shifts to blue, then purple, then gray, and eventually to a powdery white that means the weld is compromised. The quality of the work is written on the surface in color if you know what you are looking at. Now put all of that together and consider what it means commercially. Every stage of titanium frame production demands skilled human labor, careful preparation, and expensive consumables. It resists automation. It barely improves with volume. Building 10,000 titanium frames costs almost 10,000 times what building one costs. Carbon fiber works in exactly the opposite way. A mold is expensive to design and build, sometimes extraordinarily expensive. But once it exists, every frame that comes out of it is cheaper than the last. The labor is significant but trainable, and it was relocated at enormous scale to manufacturing regions where that labor cost far less. Carbon frame production gets dramatically cheaper as volume rises. And that is the whole story in one sentence. In a mass market, the material that gets cheaper with scale wins the mass market. Titanium never could, so it never did. It is tempting at this point to reach for a conspiracy, to say the industry buried a lifetime material because a frame that never dies is a customer who never returns. That incentive genuinely exists, and it is worth naming honestly. But there is no evidence of coordination, and the manufacturing explanation is complete on its own. Carbon won because it was genuinely better for the riders the industry was selling to, and because it could be built at a price the industry could sell.
Both of those are true at once, and neither requires anyone to have plotted anything. So where does that leave a cyclist standing in front of a titanium frame today, deciding whether to spend the money? The market has split into 3 tiers, and knowing which one you are looking at matters more than the word titanium. At the top are established builders in Europe and North America, welding in-house, often offering custom geometry, with frames commonly costing between 2,500 and 6,000 euros. In the middle are branded frames manufactured under contract in Asia, typically 1,200 to 2,500, where the quality depends heavily on how much engineering and quality control the brand actually applies. And at the bottom are direct import frames sold through online marketplaces, sometimes for under 1,000 euros. It would be easy to dismiss that bottom tier entirely, and it would not be fair. There is no systematic independent testing of that market. Some Asian titanium manufacturing is genuinely sophisticated, and some of those factories also build frames for Western brands. Reports from owners include both excellent long-term experiences and real failures. What is fair to say is exactly what you cannot verify when you buy that way. You cannot verify the alloy certification. You cannot verify the tube wall specification. You cannot verify what quality control the welds pass through, or whether the frame was ever fatigue tested to a recognized standard like ISO 4210, and you have essentially no warranty recourse if something goes wrong in year 4. That is the honest framing. The money you save is the cost of somebody else having checked those things. Sometimes that is a reasonable trade. Sometimes it is not.
But it should be a decision, not an accident. There is one more piece of the pricing conversation worth correcting. You will often hear that the metal in a titanium frame only costs a few €100, offered as proof that you are being overcharged. That is arithmetically true and almost meaningless. Material cost is a small fraction of the price of nearly every manufactured object. The real question is what the labor, the skill, the quality control, and the continued existence of the business are worth to you, and whether you are actually receiving them. Which leads directly to the promise that sells more titanium frames than any other, and the caveat that almost nobody attaches to it: the lifetime warranty. Read the terms, because they are narrower than the phrase implies. Across the industry, these warranties are typically original owner only and non-transferable, which quietly cancels the resale advantage you were told the frame had. They cover manufacturing defects, not crash damage, not corrosion caused by improper assembly, not modification. And lifetime very often means the reasonable service life of the product rather than the length of yours. And there is a harder problem underneath the legal language. A lifetime warranty from a small builder is worth precisely as much as that builder's continued existence. A 20-year guarantee from a company that closes in year 8 is a piece of paper. The material's actual durability is a far better guide to what you will get than the warranty document. But even that is not the real expiry date on a lifetime frame. This is. Your titanium frame will not wear out. The bicycle industry around it will move on regardless.
A titanium frame built for rim brakes, quick-release axles, a superseded headset standard, and 28mm tire clearance is limited by every one of those decisions, forever, no matter how perfect the metal remains. The frame outlives the ecosystem it was designed for. That is what actually ends the life of a lifetime frame, and it is why the single most important decision when buying one is not the brand or the welds. It is buying current standards with the most generous tire clearance you can find. So who should actually buy one? If you ride through salted winters, or near the sea, or commute year-round in bad weather, titanium's case is the strongest it gets. Corrosion resistance is verifiable, mechanical, and solves a problem you are already paying for. If you ride gravel or long endurance distances, the case is strong. Impact tolerance matters when debris hits your down tube. Mount points matter. Dent resistance matters. And the aerodynamic penalty that hurts a road racer barely registers at gravel speeds. If you genuinely intend to own one bicycle for 15 or 20 years, the case is strong, with the standards caveat attached in bold: buy the most future-tolerant specification available or the promise expires early. If you race or ride in fast groups where you are working hard to hold a wheel, the honest answer is that titanium is the wrong choice. The weight gap is real, the aerodynamic gap is larger, and both matter precisely in the conditions you ride in. Carbon is better for what you are doing, and no amount of admiration for the material changes that. And if you have a fixed budget of around €3,000 for a complete bicycle, think very carefully.
At that price, choosing titanium forces compromises on wheels, tires, and group set, and those components change how a bicycle rides far more than the frame material does. You would very likely end up with a slower, worse-equipped bicycle wearing a more admired metal. Which brings us back to where we started. Titanium is not the best frame material. It never was. It is the material with the best balance of properties in a market that stopped valuing balance and started valuing specialization, and it lost to a material that could be shaped, tuned, and manufactured in ways no metal can match. But that is not a story about titanium being overrated. It is a story about what happens when a product is optimized for durability in an industry organized around performance and scale. Titanium answers a question the market largely stopped asking. If you happen to be asking that question anyway, if you want one frame, unpainted, indifferent to weather, still structurally sound in 30 years, then the material is not a myth. It is doing exactly what it has always done. Just make sure it is the question you are actually asking, because the most expensive mistake in cycling is not buying the wrong bicycle. It is buying the right answer to somebody else's question.